All right, here is a presentation that I put together on how to take data that you get in the form of load versus extension on a tensile test and convert that to stress versus strain data so that you can calculate the modulus of elasticity and the yield strength, and if you want, the ultimate tensile strength. Okay. So there will be two ways that you'll be provided data, or you'll collect data. In one case, it might come from like a data acquisition system, and you'll just have columns of load and extension. Or you might actually get the load versus extension graph. So using those two possible forms of data, I'm going to talk about two different methods for converting that to stress versus strain. So this is method one, where I've been given a set of load and extension values. I've also been given the gauge length, in this case 63.5 millimeters, and the cross-sectional area of the sample, which was 61.1 millimeters squared. And so if I want to convert these values of load and extension to stress and strain, I need to divide load by area. I need to divide extension by the gauge length. So here's an example. I've got load as 1,400 newtons. I divide that by my cross-sectional area. I convert that to newtons per meter squared. That's a Pascal. And I've got 23 times 10 to the 6 pascals, or 23 megapascals. I've got 0.03 millimeters extension, and I divide that by the gauge length to get a strain, which doesn't have units, of 0.0005. So I can do this for all of my data and record stress and strain values according. My highest value of stress is 200. So this is a little bit messy looking. It's a hand-drawn deal, but I plotted the data and then I drew a line through the data. And you can see that we have a linear region and a nonlinear region. Okay, so now that that's drawn, I can calculate yield strength like this. For yield strength, you start a line at the value 0.002 strain, right there, and you draw that line that's parallel to the data line and watch for where it crosses your actual data, right up here. So starting at a value of 0.002 strain, drawing this parallel line. So here's the yield strength. I'm sorry, I would take that 226 as the ultimate tensile strength. Now, I also can calculate modulus from this graph. I need to just get the slope of the linear region. And I have two data points already, stresses of 23 and 46 and strains of 0.0005 and 0.0013. So I'll just use those values to calculate my modulus. 46 minus 23 megapascals, and this difference in strain, and I get 28,750 megapascals, or 28.8 gigapascals. Okay, megapascals are 10 to the 6, gigapascal are 10 to the 9th. So that's method one. The other way I might be provided data is actually the graph of load versus extension. So here I've got load values in newtons, and I've got extension values in centimeters. Here I'm also given the cross-sectional area and the gauge length. So I can take these load values, divide them by area to get stress, and I can take my extension values and divide them by gauge length to get strain. So looking just here at the 10,000 Newton load value, if I divide that by 50 millimeters squared and make sure I convert my square millimeters to square meters, I have 200 times 10 to the 6 pascals, or 200 megapascal. So where I had 10,000 newtons of load, I have 200 megapascal of stress. Do that for all of the load values on my y-axis. Then on my x-axis, because my gauge length is 2 centimeters, I can divide each of these values, which are in centimeters, by 2 to get strain. Okay. Learning how to use this, those values didn't stick. So let me draw this one more time. Start at 0.002, draw a line that's parallel to the data, the linear part of the data, and then wherever that crosses my original data line, that is my yield strength. So somewhere around 315 megapascals. I'm not quite sure what to do to make sure that stays. I don't think it will, but hopefully you can see this method. And then to calculate the modulus of elasticity, here, I'm going to just choose 2 points in the linear region to calculate slope. So this point, I have a strain of 0.0005 and a stress of just under 40 megapascal. See, that would be 20. So I'm going to call it 35 for stress. And then this data point, I'm at 0.0025 for strain. And for stress, let's see, this is about 100, so we'll split the difference and we'll call it 110 megapascals of stress. All right, so now I can calculate the slope by change in stress over the change in strain. So I've got 110 minus 35 megapascal divided by 0.0025 minus 0.0005. Okay. So my units for modulus just here are megapascal, but my number is going to be 10 to the 3 big, and so I'll convert that to gigapascal. All right, so just a couple of other points here about tensile fracture, tensile failure. There's a classic shape that the sample will form or will have called a cup and cone shape. This is the cup part of the sample. The other part will be the cone part. So what I've got here, what I'm looking at here is the cup part of the sample, and the cone part will look like that. So how does this form? Notice that there's one part of the failure surface that's kind of flat. That's this circle. And then from that point out, it's about a 45-degree angle, and this is called the shear part of the sample. And so what causes this first part of the failure to occur? In all metals, there are basically undissolved particles. We call them inclusions. And the interface between the inclusion and the metal is the first thing that's likely to separate under tension. And so it will look like this as we're pulling on the sample. The metal will delaminate or pull away from the inclusions. And assuming that the stress is in this direction, those voids will grow as the sample is being pulled, and eventually they'll line up and there will be necking in between them to the point where they become one void, because each of those little individual voids have coalesced. And once that happens, now you've formed this surface. When this surface of failure gets big enough, then from that point, failure is much faster, goes at a 45-degree angle in shear. Here's another image using electron microscope. So here is the area where failure was started with microvoids, and this is what they look like craters on the surface. And then from there out, we have our shear fracture, a much more cleaved, sort of flat surface. Okay. So that's it. I will post this, or the link to this, and then I'll also solve a couple without a video, just so you have some more examples.